Hi guys, my name is David Macy,
I'm Hannah.
and we're doing our final project on scenario C for math modeling.
In this project, we will be exploring the best possible SIR plus model for scenario C. In this scenario, recovered sick people can become sick once again, and there are carriers in addition to the sick people. We include graphs, difference equations, and sensitivity analysis for our model. Afterwards, we explore how population size and contagiousness would affect the model.
So here's our basic SRI model with no additional components, and as we can see, it's a very poor model with a sum squared error of 8 million, and our model barely follows the actual population or sick model of what's actually happening.
Here's our SIR plus model. Here you can see the curve follows the trend much better with the peak sick people matching up and matching in the end long term. Here we added carriers to our infected people, and we also added a recovered susceptible group where sick people can get sick once again. Our sum of square errors is much better with only 70,000.
Okay, so here's our system of equations for the SRI plus model, and as you can see, we made it possible for recovered people to become sick again. There's a clear significance, or yes, difference between being sick and a carrier. Or sick is you're showing symptoms, and carrier is you're not showing symptoms.
This is a start to our sensitivity analysis. First, we are comparing infection rate. When we increase the infection rate by 10%, we see more people getting sick sooner, and the peak sick population rises 5.5%. When we decrease the infection rate by 10%, we see fewer sick people at a slower rate, and the peak sick population is 5.8% lower.
So this is when we mess with the recovery rate, and when the recovery rate is increased by 10%, there are 4.9% fewer people getting sick and recovering faster, as shown in this graph, and 10.3% fewer people are sick long term. If we decrease this variable by 10%, we see 5.1% more people getting sick and recovering slower, with 12.1% more people sick long term.
Here we are comparing recovered susceptible people. If the rate that recovered people become susceptible again is increased 10%, we can see a slightly higher total infection long term, while decreased 10% shows less people sick long term. So the recovered susceptible variable decreases by 10%. There are 10.6% fewer people sick on the last day, while if we increase this number by 10%, there are 9.9% more people sick on the last day.
So here we mess with the carrier rate. This was the rate at which people became carriers versus being sick. And here we can see when we increased it by 10%, there was less sick people overall, which makes sense because if you have more carriers, then you're gonna have less sick people. And this with the decrease in carrier rate, we see that there's more sick people. As I said, the peak decreases by 9.67%. When the carriers increase by 10%, the peak increases by 8.28%.
Here we're comparing the initial number of carriers that we have in our data. This is a 10% change, but it's only resulting in a 1 person difference. When the carrier rate is lowered by 1 person, the peak of sick people stays elevated for a slightly longer period, but this is only a small difference. When the carrier rate is decreased by 1 person, the peak increases by 0.45%. When the carrier rate is increased by 1 person, the peak decreases by 0.53%, so barely any change at all.
So this is our predictive model, and we also took our infection rate for one of the scenarios. And when we made the k-value of the contagiousness times 2, and we can see the peak happens a lot sooner, and this causes about 46.9% of the entire population to actually get sick, which is not good at all. That would be terrible. And then when we have the contagiousness, we see that 18.1% of people are sick, which would be below the crisis level.
So here we wanted to see what level of contagiousness would get us at the level of crisis in our community. So that would be 20% population was sick. So our infection rate would have to be 0.0000822.
So here we tried altering the population too to see what would happen in different scenarios. And here if we double the population, we see that people get sick much faster on day 8. 47% of the population are sick, but they recover. They end up recovering also. With half of the population, far fewer people get sick at a much slower rate. Day 23, 4.6% of the population is sick. And we can see that the peak is increased by 190% with doubling the population and decreased 71.8% with halving the population.
In conclusion, our model contained 4 groups of people: the susceptible, sick, carriers, and recovered. As stated before, the recovered were still susceptible after being sick. The constants include K for contagiousness, R recovery rate, C carrier rate, and R carrier susceptible. Our model improved by 99.14% from the original SIR model. We can conclude that this model does a very good job of explaining the pandemic. We concluded that infection rate and carry rate had the biggest effect on the sick graph. This makes sense because increasing the infection rate would increase the amount of sick people, and decreasing the carry rate would increase the number of symptomatic sick people. The biggest takeaway from our predictive model is that in order to stay out of the crisis state, we need to have a K rate of 0.0000822. We also explored how doubling and halving the population would affect the sick graph. It comes without surprise that doubling the population makes a peak occur much faster, and halving the population makes the peak occur much slower. Precisely, the peak sick population increased 190% with double the population and decreased 72% with half the population.
Alright, that's our presentation. Thank you.